right, so when you filled in this two-way frequency table, what did you put for males that started driving over the age of 16? There you go. Good. 5. How about females that started under the age of 16? There you go. Total people that started driving under 16. Total people that started driving over the age of 16. And total students completely. Good. All right, moving on to the next one. Owning a cat, owning a dog. How many people own a cat and own a dog? There you go. How many total people own a cat?
14.
How many people do not own a dog and do not own a cat? 8. How many people own a dog? How many people do not own a dog? 16. Good. So, this is very algebra 1, but we're going to, of course, take it and up it today. Okay? You know how to add and subtract to fill in numbers. Okay? And then as I was asking you pieces, you were able to translate the frequency table as well. Okay? You were able to read it and define what means what. Okay? We are going to use frequency tables to introduce something called conditional probability today. Okay? So conditional probability, okay, is the probability that event B occurs given that event A has already occurred. So there's a condition. We know something about our situation. It's not just, hey, who owns a cat? It's, hey, if I know they own a dog, what's the probability that they also own a cat? So you know something. So your subset is going to change. You're not looking at the complete total of everybody. You're looking at the total of what you already know and taking it out of that. Okay? How we write that? So the probability of B given A is written probability B given A. And the A and the B can switch. It just depends on what we're talking about. Okay, but the given comes second. Yeah. So what's the probability of this happening if this is already there? Okay, so for the front, we'll use frequency tables. And then on the back, we'll see what we do when we don't have a frequency table. Our first example, we have a family that has 2 dogs and 2 cats. They randomly select a pet to get brushed, then randomly select a different pet to get a treat. Find the probability that they select a cat to get a treat given that they've already selected a dog to get brushed. Okay? So, before I even think about the probability, let's look at our possible outcomes. Okay? But if I pick a pet first, I could have a cat first or a dog first. Do we correct? Do we agree? I also have 2 cats to choose from and 2 dogs to choose from. Okay? So my first pick, it could be cat 1, right? And then I could pick dog 1. We could do cat 1 and then dog 2. We could also pick the 2 cats, correct? I could pick cat 1 and then cat 2. Those are all the combinations if cat 1 is picked first. What if cat 2 is picked first? Okay? So if I pick my cat 2, then dog 1, cat 2, and then dog 2, cat 2, and then cat 1. Those are all the possible ways we could pick my pets if my cat was first. Either cat was first. So let's look at dogs. We got 2 dogs, right? So I can pick my first dog with my first cat. I can do my first dog with my second cat. And I can do both dogs. First dog, second dog. Now let's see if I pick the second dog first. So dog 2 can go with cat 1. Dog 2 can get picked with cat 2. and then dog 2 can be picked with dog 1. These are all the possible ways to pick out of these 4 different animals. Okay? So now, find the probability that they select a cat to get a treat, given that they've selected a dog to get brushed. So what do we already know? We know a dog was picked to get brushed, which means a dog was picked first. Do you agree with that? We know a dog was picked first. So we are going to focus on just this bottom row. Okay? This is dog first. So what is the probability that our cat is picked second if I already know that a dog was picked first? That's how we show it. Okay. So how many times was a dog picked first? There were 6 times. Good. Out of those 6 times, how many times was a cat picked second? 4 of them, right? 1, 2, 3, and 4. Which will give me about 0.667, or we could say about 66.7% chance. If we know a dog has already been picked, there's a 66.7% chance that a cat can get picked next. Makes sense, right? You can't pick the same animal twice. So make sure your math makes sense. So when that one animal is gone, aren't 2 of the 3 animals left cats? Our math makes sense. What's up? Because it told me find the probability they select a cat given that they've already selected a dog. So I had to know all of my outcomes. Yeah, what are all the possibilities that could happen? And now I'm going to focus on what I already know. Mm-hmm. Yeah. All right, let's do this again with the frequency table. Okay, so that was more like what we did yesterday, right? So we did conditional with all of our outcomes. Here's a frequency table now. Okay. Quality control inspector checks for defective parts. The two-way table shows the results. Find each probability. So a defective part should fail the test, correct? A non-defective part should pass the test. But there's a thing called real life and margin of error. Okay? It's not always perfect. So this shows what really did pass, what really did fail. The first one it wants me to find is what was the probability that something passed if it was defective, right? That should not happen. So hopefully my percent is low. Does that make sense? Yeah. Okay, so let's see what happens. Probability that it passed the test given it's a defective product. So I already know it's defective, correct? How many total defective products were there? Total is 39, right? Out of those 39, how many passed the test? 3. Does that make sense? So given it's defective means I'm only looking at this row. So I know it's defective. So there's 39 of those. Out of those 39, 3 of them passed. Which is going to give me about 0.077. So there's about a 7.7 chance. 7.7% chance that a defective product will pass the test. Bless you. Part B, what's the probability if it fails, if it's not defective? So again, this shouldn't happen, right? Hopefully we get another low number. If it's a good product, it should pass the test, not fail the test. Okay? So we're looking at a new row. We know it is non-defective. So now we're looking down here. How many non-defective products were there? 461. Good. So out of the 461 products, how many of them failed the test? 11. Don't you speak too soon, friend. So, about 2.4% of products that worked failed the test. It is a low number, so that is good. It's not going to be zero. We don't live in a perfect world. I know. Margin of error is there on purpose. Okay, so using a two-way frequency table is nice. Okay? There's a conditional probability that we can, a formula that we can use. Okay? If we are not given a frequency table. So we're going to use it with a frequency table to see like how it works. And on the back, we're going to use it when we don't have a frequency table given to us. All right? So we're going to go back to our first example. And we're going to use the probability of P and A divided by the probability of just A. So we're looking at what is the probability that they passed and effective divided by the probability of just passing. I lied. Of just effective. Okay? Okay. So, probability of A and B divided by the probability of A. So what was the probability that they were that they passed and they were defective? How many did that? 3 out of how many total products? How many total products were there? 500. So 3 out of everything was defective and it passed. Okay. Divided by, what was the probability that it was going to be a defective product? There's the 39. So we can keep, change, flip. And see how it becomes the problem we just did? Simplifies the 3 over 39. Okay, so that's why that works. Okay, when we use this in a second, we're going to use it with decimals because we're not given a frequency table, we're given percentages instead. Okay, bless you. The conditional probability. What is the probability that something happens given I know something else? We do the probability of both things happening divided by the probability of what we already know happened. Okay. All right, so ready to do this without a table? Yes? Because obviously if you have a table, you don't have to do all that, right? We did the shortcut. We didn't need to do all that keep, change, flip. But that's not always going to be given to us. Okay? On the back, we have people buying lunches. You good? Okay. So here we go. We have people buying lunches. At a school, 60% of students buy a school lunch. 18% of all students buy a dessert. And then 10% of all students buy lunch and a dessert. Okay? What is the probability that a student who buys a lunch is also buying a dessert? Okay, so what's the probability that a student who already buys a lunch is going to buy dessert? Okay, so what is given? What do we already know? We already know students buy lunches, correct? So when I'm doing probability of A given B, okay? The given event was that they buy lunch. I want to know, if I know they buy a lunch, how many will also buy dessert? So probability of them doing both divided by the probability of just buying a lunch. Okay, so I don't have a table to look at, but they did tell me. Okay, what was the probability that someone bought both? 10%, and how are we going to put that into our formula, you think? Yes, 0.10 or 0.1. What percent of students buy a lunch? 60%. So how's that as a probability? We're going to use, 0.6. Oh, that should be. So 0.1 divided by 0.6 is going to give us about 0.167. Come on, pen. There we go. So we're going to say about 16.7%. So if we know somebody buys a lunch, we can say about 16.7% chance that they're also going to buy a dessert. Okay. Do you think order matters? Yeah? We're about to find out, because now I want to know what's the probability that a student that I know buys dessert, what's probably that they're going to buy a lunch. Okay? So yeah, my A and B are going to, they're the same. We're going to keep A being buying a dessert. We're going to keep B as buying lunch. Okay? So now they're flip-flopped. What's the probability that they buy a lunch if I already know that they're buying a dessert? Okay. So probability of them doing both divided by the probability that they buy a dessert. Okay, so my top is the same, right? Buying a lunch and dessert. That's still 0.1. What's the probability that they are buying just dessert? 0.18. And this is going to give me, 0.556. So about 55.6. So yes, order definitely matters, because as y'all saw, the setup changed. Our denominator did change, so that is going to change our outcome. What's up?
So like just about 45% of people don't even get lunch, just get dessert.
I don't know, maybe.
That sounds not fun.
So if we know they're buying desserts, about 55% of those are also going to buy a lunch. They're likely to. All right, last little bit about conditional probability, okay? And then we'll go do a brain break. We're almost done with this. Okay, using conditional probabilities to make a decision. So we have a jogger. She wants to burn a certain number of calories during her workout. She maps out 3 possible jogging routes. Before each workout, she randomly selects a route. Afterward, she uses a fitness tracker to determine whether she reached her goal. The table shows her data. Which route should she use from now on? So the first thing we have to do is convert her tally chart into a frequency table. So I'm going to pause and you're going to do that. Convert those tallies into the decimal, and not decimals, frequency table. Okay, so that part was given to me. What did you put for the total of reaches the goal? Alright. Total for not reaching it. 16. Total for route A. Total for route B. Total for route C. 18. Total for every... How many runs did she do? 50 runs. Right? It is. I mean, if she did it every day, it's less than 2 months, technically. Okay, so I'm going to help you with the first one, and then you and partner are going to do B and C, or someone close by. Okay, so we need to find for each one what is the probability that they reach the goal given they did route A, B, or C. Okay, so the first thing we're going to do is probability that they reach. So they reach their goal on A divided by just route A. Does that make sense? Okay, so my total, how many total times did they run on route A? 17 times, good. And out of those 17 times, how many times did they reach their goal? 11. So that's about 0.647. So she reaches her goal about 64.7% of the time that she runs on route A. Does that make sense? Okay, you do route B and route C. You were a sneak. All right, what did we get for route B?
73.6.
Okay, how did you set it up?
It's 15 totals and 11 was the goal reach.
There you go. So about 0.733, which is about 73.3% of the time that she went on route B, she reached her goal. How about on route C?
12 or 18.
Okay, set up as 12 over 18, which simplifies to 0.667. So 66.7% of the time she went on route C, she met her goal. So, time to fill in the blank. Based on the sample, the probability that she reaches her goal is greatest when she uses route B. So she should use route B from now on. Yay. This one wins. Good.